Good evening to all. I'm Sandhya, a research scholar from IIT Kharagpur. Today, in this fifth live session on payment methods, we will be discussing about the assignment 4 questions which have been submitted previously, and also we will discuss about the summary of week 5, and corresponding to the week 5 lectures, few numericals also we would be solving in this session. So you could have already seen the answers for this assignment 4. So let us quickly go through them. The first question is angularity and workability of aggregates are whether they are directly related or inversely related or they are not related is the question. If you see about angularity and workability is nothing but how much energy is required to mix the aggregates and the bitumen. So if you take any of the angular aggregates, so they require more amount of energy to mix with the bitumen. If we see the rounded aggregates, they require less energy. So workability, to make it more comfortable, aggregate should be angular, rounded in nature than angular. So they are inversely related. And if we see the second question, flakiness and elongation test is done on aggregates having the size. So if you could have remember our thickness gauge and elongation gauge, there the sizes were 63, 50. Starting from this, at the end there is one smallest size which is 6.3 mm. So any aggregate which is having the size more than 6.3 mm, and this size only we would be doing flakiness and elongation test. So why don't we need to do the flakiness and elongation test on fine aggregates? Are the aggregates whose size is less than 6.3 mm is, if you imagine the 6.3 mm size which is extremely small. So flakiness or elongation, which is nothing but the flatness, which is nothing but the how thin the material is. and also the elongated, how lengthy the aggregate is. These two are problematic only in the coarse aggregates. If you take the fine aggregates which are very small, whether those aggregates are very long or very thin, it is not going to affect the performance of the mixture. It is the surface characteristics of the fine aggregates that would affect the performance. But when it comes to the coarse aggregate, shape and length and thickness characteristics would affect the performance. Thereby, we are only worried about the sizes who is having greater than 6.3 mm in range. And if you see the third question, so they have given two aggregate sizes 19 and 4.75 mm, and they also have given the weight retained on 19 is 200 mm 200 grams, and the weight retained on 4.75 is 500 grams. So for these two average sizes, you can see the heading, they have mentioned the average size. If they could not have mentioned the average size, you are supposed to calculate the average size. Here they have directly given, so no need to worry. And the weight retained on each size is given. They are asking us to calculate the surface area. How do we calculate the surface area? In order to calculate the surface area, we need the surface area factor for 19 mm. We also need the surface area factor for 4.75 mm. If I know the surface area factor, I can multiply this weight with the surface area factor. That is what is nothing but the surface area. Then that can be done individually for 19 mm and also 4.75 mm, and that can be summed up. So if you could see here, that is what has been done. So we have calculated the surface area factor. The equation for surface area factor is 6 by GD. We know the G, specific gravity, that has been given, and also we know the D. Here D is nothing but the average size of the aggregate. Here it is given 19. So if you could have remembered the default tables of surface area factor, there was a table already mentioned in MS2. So this is a code book which is used to understand the asphalt mixture characteristics. So this MS2 version, there was a default table for surface area factors. There the average sizes has been taken. For example, if the 19 to 13.2 is the range of the aggregates, then they have taken 19 plus 13.2 by 2 as the average size. Here for you, the direct average size is directly given as 19. So you can directly substitute. So if we obtain the surface area factor, by multiplying that surface area factor with this weight, we can calculate the surface area. Then if we calculate the surface area individually, we can sum up and get 255.42. And fourth question is, which IS sieve is used to assess the amount of fines generated in the Los Angeles abrasion test? So Los Angeles abrasion is one of the abrasion tests. There are other tests also. So in this test, after subjecting the aggregates into the abrasion, at the end we take 1.7 mm sieve and we try to see and we understand how much of the aggregate is getting abraded or getting into fines. That we understand by sieving through 1.7 mm sieve. If it is impact value test, that would be 2.36 mm sieve. And if you take the fifth question, which test can be used to identify the amount of clay in the fine aggregate? So impact value test is to perform on coarse aggregates, and Los Angeles abrasion also to understand the abrasion properties of coarse aggregates. Soundness is to understand the durability property of the aggregates, especially the coarse aggregates. So if you take the sand equivalent test, if you remember, we used to take a tube, we used to add the fine aggregates with the water and we used to shake and wait for 20 minutes. Then we see the separation of fine aggregates and the clay particles. So the amount of clay particles that has been separated is what we used to understand from the sand equivalent test. So sand equivalent test was the answer. And if you see the sixth question, which experiment can be performed to study the specific surface area characteristics of clayey particles? And if you see the options, sand equivalent test, fine aggregate angularity test, particle index test, and methyl blue value test. So out of these 4 tests, in the last class as we have discussed, methyl blue value test gives the more qualitative approach of understanding the surface area characteristics of clayey particles. And if you see the 3 types of specific gravities, you can see bulk specific gravity GSP, apparent specific gravity GSA and effective specific gravity GSC. The only difference between 3 specific gravity is the amount of aggregate value that we consider. If we take the apparent specific gravity, we consider only the aggregate value. If you consider the bulk specific gravity, you consider mole volume. So, specific gravity is weight by volume. This is what density of the aggregate divided by density of water. Let us assume density of water is 1. That is the reason why this denominator we are not representing every time. Let us take the numerator weight by volume. If the G value to be high, volume should be low. That means specific gravity is inversely proportional to the volume of the aggregates. If you see the volume considered in the GSA, that is apparent specific gravity, is only the aggregate volume. If you see the bulk specific gravity, it is the aggregate volume plus the voids or pores that are filled with water. If you see the effective specific gravity, those are the aggregates that are not filled with the bitumen plus the aggregates filled with the water. So considering these volumes, we know that the apparent specific gravity is the largest, followed by the effective specific gravity and followed by the bulk specific gravity. Let us see this 8th question. Let us say that there are 2 stockpiles A and B, and also it has been told that stockpile A has 60% coarse aggregates, stockpile B has 70% fine aggregates. So by looking at this information, you might be readily wanted to calculate the specific gravity of stockpile A and B. But let us continue reading the question. The specific gravity of coarse aggregate and fine aggregate is already given here. So if you see here, the specific gravity of stockpile A and the stockpile B is already given as 2.67 and 2.72. If they have already given the specific gravity of stockpile A and B, and if they mention that 60% of stockpile A, 40% of stockpile B are finally blended together to calculate the specific gravity, then what is the specific gravity of final mixture? So you can see here, you can also calculate this like out of total 100, 60% are from the stockpile A, and stockpile A has the specific gravity of 2.67. Then 40% has stockpile B, and the stockpile B has the specific gravity of 2.672, which is nothing but the same which I have written here. And if you see the 9th question, with increase in the confining pressure, the stiffness of the aggregate particles, whether they would reduce, remains the same or increase. So if you could have seen one of the examples that has been explained by the sir in the video also. So let us say you have aggregate particles, vehicles are moving at the top. If there is no support from the sides, there is a higher chance that these aggregates will collapse because confining pressure is 0 here. If I increase the confining pressure from the sides, there is a higher chance that this aggregate can be more stiffer in stage. So the stiffness of the aggregate particles would increase if we increase the confining pressure. And if you see the 10th question, granular materials exhibit isotropic behavior, elastic behavior, cross anisotropic behavior or anisotropic behavior. Though we assume that elastic modulus or resilient modulus is a property of granular materials, in real or in practical, granular materials behavior is not that simple. It is very complex. It has the properties of cross anisotropic behavior, which means the resilient modulus in all the directions are not same. Of course, in the design currently we assume that is like a resilient modulus or elastic behavior, but in real the behavior is cross anisotropic, which implies that this modulus value is not same in all the directions, but we don't need to consider this behavior in the pavement design. And if we come to the week 5 summary, so in this week 5 lessons, we have been touched up with the basics of the bitumen, what is the chemistry of the bitumen, and what are the physical properties that need to be investigated before selecting the bitumen into the asphalt mixture pavement design. So there are different types of bitumen. Basically, what we call bitumen is usually obtained from the fractional distillation of crude oil. That means if you have the crude oil, if I distillate that crude oil, otherwise if I separate the crude oil in fractions, like I will not be separating at a time. If I have 100% of crude oil, initially 10%, 10% of the fraction I will separate, again another 20% let us say. So in fractions wise, I will separate the crude oil into separate parts. So at the end, whatever the residue that is remained is what we are considering as the bitumen. So this bitumen has been obtained from the fractional distillation of crude oil. But if you take the tar, though we call this bitumen and tar synonymously in India, this is obtained from the destructive distillation of coal or wood. This is not from the crude oil. And the cutback and bitumen emulsion, usually these two are actually obtained from this bitumen. So let us say if the bitumen is very stiff at the 25 degrees temperature. So in order to make that into the less softer, what do? We usually increase the temperature. Even in the field also, when I am going to mix these bitumen with the aggregates, I have to heat this bitumen and aggregates to a mixing temperature, let us say 165 degrees. But every time increasing the temperature of bitumen is not good for the environment. That's so people have come up with various techniques to soften the bitumen, to reduce the viscosity of the bitumen without heating. I do not want to increase the temperature, but I still wanted to make the bitumen very soft so that can coat my aggregate very easily. So cutback bitumen is one of that type of bitumen where we will be using the solvents. So I will add some solvents to the bitumen so that solvent will make my bitumen very soft, then I can actually coat the aggregates properly. And another type of bitumen is the bitumen emulsion. In this also, if I have a bigger particle of bitumen, by using a dispersed medium, I can make this bitumen into small particles. That means I am actually making them to suspend. So when I make it to suspend, what happens? So when I make it to suspend, the viscosity of the bitumen would be reduced. Here also we are not increasing any temperature to the existing bitumen. So cutback and bitumen emulsion are two of the types of existing bitumen. Let us say I have produced this bitumen from the crude oil. How do I know if I have multiple sources of crude oil, to which crude oil source I should go so that I can get the maximum amount of bitumen from that crude oil source? It depends upon the API gravity, which is nothing but the American Petroleum Institute gravity. If we see this formula, it includes the specific gravity. So if the crude has the specific gravity value high, if the specific gravity is high, API value will be low. When I say specific gravity is high, that means the molecular weight will be high. When I say molecular weight is high, means the residue would be more. As the residue is more, the yield of the bitumen would be more.
Excuse me, madam. What is this yield means? What is this yield?
Yes, sir. So when we go to the next slide, I will show the production process. In that we will see what is the yield of the bitumen. See, if you come here, let us see. So in this chamber, initially you have petroleum or crude oil. So we will be extracting the petroleum, gasoline, all those fractions. So after converting this crude oil with the temperature of, let us say, 350 to 380 and also to the atmospheric more than atmospheric pressure. So whatever is lighter in weight, they will be evaporated or they will be collected at the top. But few of the particles which are having higher weights and also which cannot be actually evaporated, they will be remained here at the bottom. That is actually called as the long residue. So we take this long residue taking this long residue, again we subject that long residue to around 350 degrees at zero point 0.1 bars pressure. Then at the end there is some remaining thing which is called as the short residue. So this is the short residue which is having the probability of bitumen, the bitumen which we actually wanted. So this short residue, let us say if I take the source 1 of crude oil, the API gravity can be, let us say, 1. If I take another source, so this vacuum residue or short residue, API gravity can be different. Let us say minus 0.7. The range of API gravity usually varies from minus 1 to 1. Okay. So if the API gravity is low, that means we have higher yield. That means this vacuum residue whatever is here has more probability of our craving grade bitumen, because this vacuum residue or short residue can have a combination of not just the bitumen, any other components. But I do not want to process that residue because it would be economically not feasible if the bitumen content is not expected. So we wanted to understand the API of this vacuum residue. Based on the API value, if source 1 and source 2 are there, if the API of source 1 is less, then I can choose this, because that implies that this vacuum residue has higher probability of paving grade bitumen. So this vacuum residue again further will be processed to get the required viscosity, whether it can be VG 30, 40, modified bitumen. Based upon our stiffness, we will be processing that. So let us say we have processed the bitumen. Though we have processed the bitumen from the different various sources, the combination or composition of that bitumen will not be same. So if I take the bitumen, the kind of elements present, mostly they are of carbon, hydrogen, and the remaining sulfur, oxygen, nitrogen, whatever are there, these are called as heteroatoms. These heteroatoms are actually the main atoms or the elements that actually will be helping us to interact with the aggregates, because we know that aggregate surface has different kind of minerals. So these minerals have some active elements or molecules. So they are active, few of them. We need some of the heteroatoms or active polar groups from the bitumen, so that they both will interact and form a good adhesion. That means good bonding between aggregate and the bitumen. So these heteroatoms are the polar elements that are mostly used to form a good bonding between aggregate and bitumen. So if you take these elements can form a straight or branched molecular structure. Otherwise they can be in saturated rings, or they can be of aromatic types. So these are the three possible types of molecular structures using these elements. There can be multiple, but these are predominant. So if you see the heteroatoms, let us say oxygen, sulfur and nitrogen, these are the polar functional groups. So in addition to this polar functional group, the other atoms or other elements which are non-polar, that means which are not involving in any chemical reaction, they are also important, because let us imagine there are a lot of non-polar but only little polar groups, because that imbalance will not be useful. Let us say you have few polar groups like oxygen, sulfur and nitrogen, they would be dispersed. You need a medium to disperse them. So non-polar groups acts as a dispersing agents for the polar groups. So the amount of both non-polar and polar groups combination is important. So in brief, if we wanted to understand what exactly bitumen consists of, so bitumen usually have a lot of molecular and elemental composition. So if we divide them, they can be divided into asphaltenes and maltenes. So you just remember the SARA fractions. S means saturates, aromatics, R means resins, and A means asphaltenes. So bitumen has SARA fractions: saturates, aromatics, resins and asphaltenes. Out of these four fractions, saturates, aromatics and resins, these three are called as maltenes. Asphaltenes are asphaltenes. So when I say maltenes, these are kind of a medium. Let us say liquid kind of medium. So inside these maltenes, the asphaltenes will be presented. So in order to make the asphaltenes in stable condition, we need the peptizing agents maltenes. So this maltenes is a combination of saturates and aromatics. Saturates and aromatics are also called as oils. Okay. So these two are oils and this is the resin and asphaltene. And one thing to understand is these saturates and aromatics, these two are actually non-polar in nature. Resins and asphaltenes are polar in nature. When I say polar, they can actually react with the aggregate surface. Among these resins and asphaltenes are more polar in nature. So any kind of bitumen that is having higher asphaltene has the higher probability to react with within the bitumen molecules and also with the other aggregates and other molecules or environment. So let us see very briefly about these components. The first one is saturates. So as I have shown the molecular structures previously, those molecular structures which are branch or straight chains, these kind of the molecular structures are actually saturates. So they are non-polar in nature. They are oils. When I say oils, what happens? When we expose these oils into the higher temperature, there is a probability that that oil could be evaporated or that oil can be easily reacting with the easily can be converted into other forms. And the amount of saturates in the total bitumen, let us say bitumen is 100%. In that 100%, there is a probability that 5 to 20% can be saturates. And if you take the aromatic, which is in the SARA fractions, the second A, this is the aromatics. So these are actually the dispersing medium. So as I told, these three are maltenes and these asphaltenes are actually present within these maltenes. So out of this SAR maltenes, these aromatics represent majority portion of the dispersing medium because they are 40 to 60% of the entire bitumen, and these aromatics are non-polar with high dissolving capacity. Okay. And when it comes to the resins, so resins are like semi-solid. So when I say semi-solid, usually bitumen is also semi-solid in nature. So when you heat the bitumen, what happens? It will be behaving as a fluid. When you solidify it, the bitumen, it acts as a solid. That means at higher temperature it is fluid in nature, at lower temperature it is solid in nature, in the intermediate temperature it is viscoelastic. Okay, that kind of behavior usually bitumen gets from these resins, because resin also behaves in the same form, fluid when heated, brittle when cooled, and this also has polarity. As we have discussed in the SARA fractions, these resins have the polarity in nature, asphaltenes also have the polarity, and these are the peptizing dispersing agents for asphaltenes. We know these three are the dispersing agents or peptizing agents, but out of these three we know A is the aromatics are the major portion, because the amount of resins is 15 to 25% only. And another important thing is on oxidation. That means these resins being polar in nature, so they have the capability to react with any other polar molecule. Let us say these resins, when they have reacted with oxygen, so they can be converted into asphaltenes. So on oxidation, they yield asphaltene like molecules. So the balance between the resins and asphaltenes is important for appropriate dispersion of asphaltenes. Okay. And the last component of the SARA fractions, which is asphaltenes. This is actually the higher molecular weight component. So if any bitumen having higher asphaltenes, that implies that that bitumen is more stiffer in nature. That means the bitumen has more viscosity, and they have 5 to 25 percentage and they can be precipitated by non-polar solvents. Let us say if I have a bitumen has 4 fractions, Sara fractions. I wanted to separate only asphaltenes. So they will not be dissolved in any kind of the solvent. They can be precipitated. That means they can be separated like solid particles. So when I mix bitumen with N-heptane, you can see a solid particle precipitating at the bottom that can be filtered out. That is nothing but the asphaltene. It has the highest polarity. So the bitumen with the highest asphaltenes can be having higher reactivity in nature. So they have high tendency to associate and interact with anything, either aggregate or any other molecular structure. So these are the viscosity building components. So any kind of bitumen having lower asphaltenes, that means that bitumen is softer in nature. If I use that bitumen in the asphalt mixture preparation, what happens? The mix will be tender. Tender means very soft. So if you could see in concrete the slump test, any concrete that is very tender, what happens? Slump will be very more. In the similar way, any kind of bituminous mixture with low asphaltene content will lead to the tenderness in the mixture. So based upon the amount of Sara fractions present in the bitumen can be actually defined as either solution type or gel type. So when I say solutions, you have Sara fractions. If you have sufficient amount of SAR, so in that SAR medium, usually asphalt will be present. That means the stability of asphalt depends upon the SAR. These are the maltings. Let us say there are no sufficient SAR fractions. Then what happens? Asphaltenes are very high. Then all the asphaltenes come close to each other and they will be flocculating. So when all the amount of asphaltenes come close to each other and they flocculate, coagulate, what happens? That will form into a very stiff bitumen. So if we have sufficient amount of maltines, they can make the asphaltenes in far distance. So in the solution type, what happens? These resins or maltines keep the asphaltenes highly peptized. When I say highly peptized, highly dispersed. So that is the Newtonian behavior. Newtonian behavior means what? At more than 100 degrees or 130 degrees, bitumen will be like fluid in nature. So that kind of behavior is called Newtonian behavior. So this kind of behavior is usually based upon nitrogen bases present in the asphalt, which are responsible for that. When it comes to the another type, which is called as gel. So if I don't have sufficient amount of resins or maltines, what happens? This non-Newtonian behavior are the asphaltenes coming close to each other and forming like a gel. So gel having higher viscosity, solution is like liquid or water. Okay, that will have lesser viscosity. So if you can see here, so in the solution type, what happens? Asphaltenes, here you can see one set of asphaltenes are here, another set of asphaltenes are here. Actually these two asphaltenes are separated by, see, these other colors which are nothing but the maltines. Let us say if you don't have sufficient maltines for these asphaltenes to separate, then what happens? All the asphaltenes will be coming close to each other and they will form the gel type of structure. So at any time, if I wanted to separate these 4 fractions from the bitumen, so there is a chromatographic separation technique. Let us say if I have bitumen. So we know that from bitumen, we can actually separate the asphaltenes by precipitation. So we add N-heptane to the bitumen, then we will get asphaltene separated. Out of the bitumen, if I separate the asphaltene, whatever present other than asphaltenes will be the remaining SAR fractions. So now I have that liquid. I will take that SAR liquid, then I will use the N-heptane again. Then whatever is separated first will be saturates. Again I will take that same solution. So because I have already separated the saturates, now that solution will have A and R. So let us use the toluene and separate the aromatics. Then whatever left at the bottom will be resins. This process is called as chromatographic technique. So we need to actually investigate the aggregates before using into the bituminous mixture. The very important tests to be conducted, which are physical tests, are one is the consistency test. So how fluid the bitumen is when it is subjected to different temperatures. Because if you see the set of consistency tests, one is the penetration, we perform at 25 degrees. 25 degrees is nothing but the intermediate temperature. And when I say intermediate temperature, let us say 25 degrees. And at higher temperature, when I say it is 60 degrees is our summer temperature. 25 degrees is our normal temperature. Let us say 25 and 35 degrees. And 135, 165, these are the mixing and compaction temperatures. Okay. So softening point which we perform at 60 degrees, this is a different temperature. And ductility we perform at 25, and the viscosity we perform at multiple temperature, 60, 135 and 165. So these are the four kind of tests to understand the consistency of the bitumen. And in addition to that, we also have durability test. Durability means if we purchase any item, what do we do? How much durability that item can give. That is called warranty. So today I have purchased an item, it has the 100% working in condition. So after 1 year, is the performance is same or it is going to degrade? If it is going to degrade, how much is it going to degrade? That is what called as durability. So before using the bitumen, we need to estimate what is its behavior or performance after 1 year, let us say, after 7 years, after 10 years. Those kind of analysis can be done using durability test. And another is a purity test. So everybody has Vg30, let us say. But how pure my Vg30 is? Does it have any impurities? So if you take the carbon disulfide and trichloroethylene, these are the two solvents in which bitumen can be dissolved. If our bitumen is very pure in nature, actually they have to get completely dissolved. If there is something that is not getting dissolved, that means impure. And another kind of test is a safety test. So each bitumen has a different kind of temperature susceptibility. So when I subject my bitumen to different temperatures, they caught fire. Sometimes they can flame the fire. So at what temperature? If I have Vg30, it can catch the fire at a particular temperature. If I have Vg40, what are these Vg30 and 40 will be discussed in the upcoming lectures. Okay, these are like kind of grades of the bitumens. So while working with these type of bitumens, we need to make sure that the safety temperatures, so that we will not heat the bitumen beyond that temperature. So safety tests are useful for that. So if we quickly go through few points which are to be remembered. Now we are not going through the detailed process. So in the penetration, let us say if I have a bitumen, and if I have a bitumen, I want to take a needle and I want to attach 100 grams of weight, and I wanted to see if my bitumen is very strong, this needle should not go very far. If my bitumen is very soft, this penetration will be more. So if I have two kinds of bitumen, based upon the amount of penetration, we can say which bitumen is stiffer in nature, which is softer in nature. So this actually will be performed for 5 seconds at 25 degrees. Okay. So according to the previous researches, if the penetration is very less, when I say penetration is less than 20, that means that bitumen is very stiff, very hard. What is the one of the problem if the bitumen is stiff? We also have the advantage if the bitumen is stiff. What? If the bitumen is stiff, when the vehicle is moving over that pavement, it cannot get deflected, which is nothing but the rutting. Rutting can be avoided if the bitumen is stiff. But let us imagine if the bitumen is very stiff, then what happens? If you have a very strong wooden piece, then if you try to apply the load here, what happens? There is a probability of undergoing cracks. In the same way, that is due to the bending. Pavement should not be stiff, too much stiff, so that it will give the cracks. So penetration, if it is very less than 20, that means serious cracking will be there, because we are testing this at 25 degrees. Let us say if I test any bitumen at 60 degrees, and at 60 degrees if the bitumen is stiff, I am fine with that, because at 60 degrees the critical failure is rutting. At 60 degrees pavement can be very soft. When the vehicle is moving over that pavement, there is a probability of rutting or depression. So, but at 25 degrees, because you are performing penetration, less than 20 means serious cracking. If it is 20 to 30 means some cracking will be there. If it is more than 30 means good resistance to cracking. Here we are talking in terms of only cracking. So, in addition to the penetration test, another consistency test is the softening point test. Okay. Let us say if you see the bitumen initially, how does it look? It looks like a semi-solid or a stiff material. So if I start heating that bitumen, what happens? That semi-solid will be converted into a liquid. This is called as a phase change. So at particular temperature, if you have VG30 kind of bitumen, maybe at 45 degrees, it could have started converting from semi-solid to liquid. But if you have more stiffer bitumen, let us say VG40, it may take higher temperature, let us say 56 degrees, to convert from semi-solid to liquid. So this temperature at which, so what is the criteria? So usually we take the, if you see here, so we take the rings, we actually fill the bitumen over here, we fill the bitumen, over that we keep these balls here. So the weight of balls we are placing on the bitumen. Then we will bring those two rings and keep here. Okay. Then here actually liquid is there, water. So we start increasing the temperature 5 degrees centigrade per minute. So it will keep increasing to 40 degrees, 45 degrees. With the time, what happens is this ball, water we are placing over the bitumen, it will try to move from top to bottom. And at the bottom, there is actually a solid steel plate, and this distance is actually 2.5 centimeters. So to travel 2.5 centimeters from top to the bottom, it takes some time, and also it happens with increase in temperature. So let us say for one kind of bitumen, it can happen at a particular temperature T1. For another kind, it can happen at T2. So we note down that temperature. We do that temperature. We recognize it as softening point. And another kind of test is the ductility test. So what we are going to here, we actually prepare a sample like this. This is the mold for ductility. We pour the bitumen here, we trim it, then we try to pull this mold from one side, at 25 degrees. Then what happens after a particular amount of pulling, you can observe a breakage here. So if we could able to stretch more time, that means the ductile properties or the coating properties, the viscoelastic properties are more for that bitumen. We do not want the bitumen to suddenly break, because that would be very brittle in nature. So these are the tests that indicates the consistency of the bitumen. And if you understand the viscosity of the bitumen, viscosity is nothing but its resistance to flow. So why do we need to understand this? When I try to mix my bitumen with the aggregates, it should not be very difficult for me to mix with the aggregates. It should be very easy. When will it happen? If we have the very lower viscosity. But the viscosity should not be very low in such a way that when I start mixing with aggregates, the bitumen will be flowing through the air voids. So we should have sufficient viscosity. So to understand this resistance to flow, which is nothing but the viscosity, we can perform this test at three or multiple temperature. So to understand the behavior of bitumen in, let us say, summer, so maximum temperature that pavement can be subjected to is around 60 degrees. So we can choose 60 degrees as a criteria. Let us say if I want to understand the behavior of the bitumen during mixing. So during mixing, we heat the bitumen to mixing temperature, let us say 160. So or 135. So based upon the requirement or application, we test the bitumen for the viscosity. So here capillary viscometer is what you see here. So we try to fill the bitumen from this. So we try to fill till this mark and also this mark. So after filling, here this side we try to apply a vacuum. What happens when I apply a vacuum? This bitumen from bottom tries to come to the top. So when it tries to come to the top, then what happened? Initially it will take some time to travel this distance. So when the bitumen is here, we will start the stopwatch and vacuum will be applied. So after a particular amount of time, you can see that bitumen is reaching here. Then we will stop the stopwatch and we will understand the amount of time. We will note down the time. So if I know that time, let us say time is T2. So this is the time T2. If I multiply that amount of time required for the bitumen to move through that bulb with the calibration factor, the theta 1 by T1 is nothing but the calibration factor. So for each capillary viscometer, currently we are working with the bitumen. Let us say there must be some standard fluid. For that standard fluid, the amount of time taken will be already calculated from the manufacturer. They will provide this viscosity also they will provide. Directly the ratio of these two, usually they give it as the calibration constant. So we need to multiply our time with the calibration constant, then we will get the viscosity of our bitumen. So if you perform this test at 60 degrees, we are actually applying the vacuum because we wanted to move the bitumen from bottom to top. When I am moving bitumen from bottom to top, that is against the gravity. That's why we are applying the vacuum. Let us say if you have 135 degrees or 165 degrees, you do not actually require as much as vacuum like other temperatures, okay? Because at 135, 165, usually the bitumen would be very soft, so you do not require a lot of vacuum. So then if we already have the capillary viscometer, then what is the purpose of going to another viscometer? So let us say if you could have seen previously the glass tube, so in those tests are usually applicable for unmodified binders. When I say unmodified binders, they are not that much stiff enough and they do not have any additives in it. But nowadays, because of the increased heavier traffic loads and also higher temperatures, we are moving towards the modified bitumens. So these are the modified bitumens which are more stiffer, and also we are going to add some additives to the bitumen so that we are modifying the properties in such a way that they can perform better. For these type of stiffer bitumens, when you try to fill that into the glass tube in the capillary viscometer, they used to choke, they used to get stuck. So when you do the repeatability, what happens is you could not able to get the similar results. So there was the error observed in those results. That's when we have come up with the rotational viscometer. So in the rotational viscometer, we fill the bitumen here, then we insert a spindle into this. This is actually the kind of spindle you can see. Then we try to rotate the spindle. So when I try to apply some torque and rotate, if this bitumen is very stiff, I have to apply more torque. If the bitumen is very soft, I can apply very less torque. So depending upon the stiffness of the bitumen, the kind of torque required to apply would be calculated. This would automatically calculated from the equipment. So based on this concept, the viscosity or the stiffness or resistance of the bitumen can be determined. So in addition to the calculation of viscosity, the other purpose of this rotational viscometer is the calculation of mixing and compaction temperature. Every time we are talking about we are mixing the bitumen with the aggregate. So at what temperature I am supposed to heat the bitumen or the aggregate so that there can be a proper amount of mixing or there can be a proper coating of bitumen over the aggregate surface. Initially we need to actually evaluate or investigate that mixing and compaction temperature. Let us say I have coated my aggregates completely. Now at what temperature I need to take this mix to the feed and use the roller to compact. So that at this temperature when you compact the mix, you can have a perfect compactness or perfect density and the perfect amount of air voids that are required in the field. So in order to calculate the mixing and compaction, the concept used is, let us say we do the test at, let us say, two temperatures. So I have performed the test at 130 degrees, then I have calculated the viscosity using the rotational viscometer. Then I'll do the test at 140, 150. You can do it at multiple temperatures. So if you have the temperature and viscosity, then you can draw a line. Okay, this is the graph can be plotted. So in this line, so these are all the viscosity points. So according to the MS2, you just select this viscosity 0.17 plus or minus 0.02. So here 0.17 plus or minus 0.02 means 0.17 plus 0.02. This is one condition, and 0.17 minus 0.02 is another condition. This would be 0.19 and this would be 0.15. So this is the range of viscosity bitumen should have so that you can mix very well. So corresponding to the 0.15, what is the temperature? It is more than 160. Then corresponding to the 0.19, 0.19, what is the temperature? So these are the two temperature ranges for mixing. So if you could able to maintain these two temperature while mixing, you can ensure that the mixing of bitumen would be proper. And in the same way for compaction also, the ranges given are 0.28 plus or minus 0.03, which is nothing but 0.25 and 0.31. So for these corresponding viscosities, what are the temperatures? We will calculate those temperatures, and those temperatures are used as the compaction temperature. So in order to calculate these mixing and compaction temperatures, usually we use rotational viscometer. Okay. So of all these tests, what is actually varying is mostly we are going to understand the susceptibility, temperature susceptibility of binder. In addition to that, the load will be applied. So to understand this temperature susceptibility, why are we too much worried about temperature susceptibility? Because bitumen is a viscoelastic material. That means it is not elastic, it is not viscous. It is both. At lower temperatures, it is very stiff, that means it is like elastic, and at higher temperature, it is like a fluid viscous. But in intermediate temperature, it is like viscoelastic. It has both properties. So it is having a range of lower temperature to higher temperature. So the susceptibility is very much important to understand. So is there any basic test or the combination of physical properties using which we can understand this susceptibilities? One of the test is penetration index. We know that penetration test we perform usually at 25 degrees. So let us see, if I want to understand the susceptibility, it also suggests that you can actually perform the penetration at other temperatures like 4 degrees. So penetration ratio is another thing. Usually Indian standard suggests one is you perform the test at 25 degrees, you perform the test at 4 degrees, and you see how the behavior is changing when we change these two temperatures. That is one of the process. In addition to that, there is another thing called penetration index. So if you see this penetration index formula, so this is an empirical. So this penetration index has a term called A. A is nothing but a slope. Which slope? Let us say if you plot a graph where the penetration and the temperature. Temperature, let us say on x-axis, log of penetration on y-axis. So the slope of that would be actually, so if the penetration temperature is increased, penetration can be reduced. The slope of that will be A. So if you know that slope, usually you can calculate the penetration index. So this penetration index calculation considers two things. So if you come to the calculation of A, one is penetration at T1. T1 is nothing but the 25 degrees usual penetration. Another penetration is penetration at softening point. So we know the softening point, let us say 50 degrees is my softening point. So you conduct the penetration test at 50 degrees. That is one option. Otherwise, the assumption is that at softening point, the penetration is assumed as 800 value. Though it is empirical because it will not be constant for all the bitumens. That is one of the fault here. So then you calculate the penetration at your corresponding softening point. Then this T1 minus T2 is nothing but, let us say our 50 degrees is softening point minus 25 degrees is penetration, the different, and their penetration differences. So using that you can calculate the A value, substitute the A value, you will get the Pi. If the penetration index is low, that means more susceptible. When I say more susceptible means, if I change the temperature, properties are going to vary very significantly. In addition to the temperature susceptibility, another important thing is stiffness of the mix. So initially, though we are discussing about the properties of bitumen, why are we even discussing about the bitumen? Finally, our interest is when I use this bitumen into the mixture. I use this for the laying the pavement. So mixture properties, mixture stiffness, mixture performance is our final goal. To understand that mixture performances, we are understanding the properties of aggregate separately, properties of bitumen separately. So to understand the stiffness of the mix, stiffness of the binder is one of the criteria to be considered, and also the volumetrics. Volumetrics are nothing but if I have the mix. When I say when I have the mix, that means aggregates in between bitumen are there, in between there will be some gaps also will be there. So aggregate bitumen and the gap together will give some volumetrics. When I say volumetrics, what are the percentage of air voids, what are the percentage of BMA, all those characteristics, and so those will be discussed when we come to the mixture test. So based on these two, usually you can calculate the stiffness of the mix. So every time it is extremely difficult to conduct the stiffness of the mix test in the laboratory or the field. So thereby from the past researchers, there are few empirical methods to understand the stiffness of the mixture. So one is Van der Poel's method, where based on the softening point and penetration index, the stiffness of the bitumen can be determined. Once if you know the stiffness of the bitumen, there are few nomographs. Nomographs are nothing but like charts. Those are based upon the past research data. Based on that, you can actually determine the stiffness of the mixture in the in theoretical. They may not be exactly same in the field. So this Van der Poel theory is again updated by two other researchers. Then using the nomograph, the stiffness of the mixes they used to calculate. So in addition to that, the other kind of tests are the durability test. So as I already explained, durability is nothing but what is the performance after few years. I know the performance of the bitumen today. So after few years, what is the disadvantage after few years? As like human beings, we get to age. So the way how we look in the childhood would be different after few years because we are getting aged. In the same way, as bitumen gets aged, its capacity will be reduced, its performance would be reduced. So what is the quantity percentage of change in the performance with age? That can be quantified based on aging. So this bitumen, when is the probability of getting aged? Initially, if I have a bitumen in the drum, that means that it has been exposed to environmental temperature, let us say 30 degrees. Then I am going to add this bitumen with some aggregate. How do I add? I usually increase some temperature. So whenever bitumen is subjected to some temperature, then there is a chance of aging. Let us say I have subjected to heating, that is the production. So in the production there can be a chance of aging. After producing, what I will do? I would be laying the pavement, then vehicles will be allowed. That is what nothing but the in service. So during the in service also, aggregate and binder combination, which is nothing but the mixture, will be exposed to the air, atmospheric air. Whenever any item, any organic material, our body is made up of organic material. So in the same way, bitumen has the polar components, organic polar compounds, which has the ability to react with the oxygen. Thereby, sometimes they can degrade, otherwise they can form extra compounds, which is called as aging. So they can become more stiffer. So during in-service also you can see some aging. So the organic molecules that are affected by the presence of oxygen. So one is due to the presence of oxygen, another is UV radiation, which is the heat, and also the changes in the temperature. So though there are more than 15 factors that can affect the aging, not each factor is very much important. So we would be considering only few factors. Let us say four. One is oxidation. When I say oxidation, reaction with the oxygen. Another is volatilization. This happens when we expose the bitumen to the higher temperatures. The oils or lower molecular weight compounds will be evaporated. And the third is the steric or physical hardening. This actually happens at ambient temperature. And the fourth is the extrudation of oils. These are the four we will briefly discuss, and then we will see few questions based on these concepts. Let us see oxidation. So bitumen with oxygen will produce polar group. Okay, let us say I have bitumen. When I expose that bitumen to the oxygen, they will produce some polar group with oxygen, and they form micelles. That means they agglomerate and they increase the viscosity. So this oxidation, usually what do they form? When I say they are forming polar groups, they are carbonyl groups like carboxylic acid, and they have higher molecular weight. When I increase the molecular weight, they will be increasing the viscosity. So how fast my oxidation will be? That means degree of oxidation, it depends upon temperature. So at what temperature I am exposing my bitumen to the oxygen, and period of exposure. How much time am I exposing this bitumen to the oxygen, and the film thickness. If I have a aggregate, around this aggregate, if the thickness is very small, the kind of oxidation it will undergo is different. And for the same aggregate, if my thickness is very thick, that means only top portion can be exposed to the aging. The remaining thickness may not be exposed to the bitumen. So the amount of film thickness also plays an important role. So another important factor is the volatilization. So the lower weight oils, they get evaporated when they are subjected to higher temperature. So it mostly is a function of temperature and exposure condition. So in addition to the temperature, is there any UV radiation and other pressure exposure, they will be affecting. So if you take the dense graded mixtures with the higher film thickness, as we have discussed previously, aggregates with a higher film thickness will be having lesser loss of volatiles. So let us see this third physical hardening. Let us say my bitumen has not been subjected to any kind of temperature and any pressure or any other external factors. Still, if you keep storing your bitumen in a drum just at normal room temperature, there still is a possibility of undergoing aging. This is called as steric hardening or physical hardening. Why does this happen is, if you take the bitumen, it has Sara fractions. In this Sara fractions, R and A, resins and asphaltenes are the polar groups. When I say polar groups, they are the active groups, they can interact and they will form some other molecular structure or they can reorient. So when I just store the bitumen, the resins and the asphaltenes, which are the polar groups, they have the heteroatoms attached. So any group that has the heteroatoms attached, they are active in nature to react. So these molecular groups, they interact among each other. Resins among asphaltenes or asphaltenes, they interact among each other and they reorient and they increase the viscosity. So this is a temporary process. So every time when we take out the bitumen from a bigger drum, what do we do initially is we heat the bitumen, not to very high temperatures, to the, let us say, mixing or working temperatures. When you heat this bitumen, usually this physical hardening or steric hardening can be reversible. That means whatever is the initial orientation of these Sara fractions in the bitumen, they will be coming into the original condition. So this physical hardening is not a problem. And another rare condition is exudation of oils. So as we have discussed in the Sara fractions, this saturates aromatics and resins. So there are lighter oil fractions. These oil fractions can be usually evaporated. That is what we have discussed. Let us say if the aggregates used in the mixture are of more high porosity. That means they have more pores on the surface. So when we mix the bitumen with these aggregates, there is a chance that these oils which are lower molecular weight they have lesser viscosity, thereby they try to penetrate into the aggregate pores. So aggregates will have the tendency to absorb them. That means now what is happening? The oils from the bitumen are being exuded or separated to the aggregate. So when the oil fraction is removed, that means whatever softer fraction of the bitumen is getting eliminated, that is being transferred to the aggregate. Now what happens? The bitumen doesn't have that softer content. Then bitumen will be stiffer in nature, thereby its aging will be occurred. So this exudation of oils is one of the factor. So if you see the summary of aging, so this aging can be a function of temperature. Sometimes if it is higher temperature, higher aging can be expected. Type of plant. Where are you usually mixing your aggregate and bitumen? If you are mixing in a very open temperature where oxygen is completely exposed, then there is a chance that bitumen can react with the oxygen and form more aging and film thickness. If your aggregates are having higher film thickness, lesser chances of aging. And the air voids. Let us say you have mixed and you have already placed your mix in the field. Now you are allowing your equipment onto the pavement. In between aggregates, coated aggregates, if the gaps are more, air voids are more, then what happens? Air can circulate from top to the bottom or within the air voids. When there is a circulation of air, there is a probability of this aging. And another is exposure of UV rays and the position of mix. So if you take the asphalt layer, this is the, let us say, top layer and this is the bottom layer. Top layer has the more probability of exposing to the atmospheric oxygen, thereby that can get aged more compared to the bottom layers. So what is the effect of this aging on my SARA fractions? Saturates, aromatics, resins and asphaltenes. So initially, if you see the asphaltene content, asphaltenes are increasing. If you see on x-axis, this is like service in years. Let us say at 0, I just laid my pavement. That means I have compacted my pavement. Rollers have come, they have laid the pavement. So from now onwards, my service starts. That means after this 0, I will allow the vehicles to move. So let us say till 14 years, I am allowing the vehicles. So this before 0 is the process where we are mixing the aggregates with the bitumen and we are transporting that mix from the mix plant to the field and we are using the rollers to compact. So during this process, what happens? The bitumen is subjected to higher temperatures. When the bitumen is subjected to higher temperatures, this saturates, which are lighter weight in fraction, and the oils, what happens? Their amount will be reduced. What happens? They will be either evaporated, otherwise the aromatics and resins, which are also lighter in fractions, maltines, they actually can be converted into asphaltenes. So you can see there is an increase in asphaltenes, but you can see a decrease in the aromatics and resins. So initially that is what happens. So as you after particular amount of years, that means you have already placed. So because initially the bitumen is subjected to higher temperatures for more number of hours, this probability can be seen significantly. As the service life is increasing, let us say now I have already placed the payment. Now there is less chance that my payment would be subjected to 100 degrees, 150 degrees. Now whatever the payment that has been laid, the probability of that subjecting to what temperatures it can, let us say 25 degrees it can be subjected to 35 or mostly 60 degrees in summer. So these are the probable temperatures. So in these temperatures, the change in SARA fractions is not that significant. That is what you can see. The change cannot be that significant. So before service only you can see the increase in the asphaltenes and also the decrease in the saturates and aromatics. So sometimes you can also see the increase in the aromatics and resins. This is because the whatever decrease in the saturates will be converted into the aromatics and resins. So let us say Now you have a pavement, so that has been in service from 0 to 14 years. When I say 0, here we have already compacted the pavement, we are ready to allow the vehicles. So now I know the properties of my bitumen at this stage. I wanted to know the properties of my, let us see, usually we know the properties at this stage. Even before laying also, what is the properties we already know. So now we have mixed with the aggregates and all. Then we have placed the pavement. At number 2 also, we wanted to understand the change in the properties. Definitely the properties will not be same because it has been exposed to the temperature. Now I wanted to understand the properties at stage 2. Let us say another thing is after laying the pavement, after 7 to 10 years, I also wanted to understand the properties of the bitumen. How do I understand? We can't every time lay pavement and go check the properties. I wanted to test this even before laying into the field. So in the laboratory, I wanted to see what are the properties of my bitumens after laying in the field and after 10 years, let us say. So is there any simulation process in the laboratory that can simulate the aging of bitumen initially after placing and the aging of the bitumen after 8 to 10 years? So there comes the process of this short term aging. When I say short term aging, initially when we mix aggregates to the bitumen and we transport from our plant to the field, so we just compacted the asphalt mixture in the field. Till that time, whatever is the amount of aging the bitumen has been subjected to is called as the short term aging. That is the reason why we named it as short term aging. Aging has been done in a short term. So this happens during the mixing and compaction stages. So how do we simulate this? So there is something called thin film oven, one of the equipment, where you can see there is a plate. In that plate you can place the bitumen of 50 grams. So when I spread the 50 grams bitumen, it will have a particular thickness. We subject this bitumen into 163 degrees at 5 to 6 revolutions per minute for 5 hours. So how did we come across this process is, let us say there was the initial bitumen, we could have calculated its properties, then we have laid the pavement, then compacted, everything was done. Then we can take that asphalt mixture, we can actually extract the bitumen from that mixture, then we can test the physical properties like penetration, softening point, all those things. Let us say in the field now currently we have the properties of the bitumen after laying. Now I wanted to create a laboratory process. So people have studied that if I take the 50 grams of original bitumen subjected to 160 degrees for 5 to 6 revolutions per minute and 5 hours, then if I test the physical properties, these properties are actually similar or near to the similar results of that we have extracted from the field. That's when these test criteria have been formulated. So thin film oven is one of that process, and in addition to the thin film oven, we cannot every time wait for 5 hours to understand the short term aging. That's when the another form of thin film oven test is the RTFO, which is nothing but the rolling thin film oven. So the difference is here you will have a rolling bottles. So you fill the bottle with around 35 grams of bitumen. It coats like a thin film around the glass surface. Again, you place the bottles at 163 degrees and we try to expose these bottles to the 4 liters per minute pressure and 15 revolutions per minute for 85 minutes. So under these circumstances, after 85 minutes, you take the bottles out and collect that bitumen into one container and now test the properties. Now we say that this bitumen has the properties after laying in the field. That means it has been subjected to the short term aging. We can see this is how we place the bottles into the RTF. So let us see if I want to understand the properties of bitumen after 7 to 10 years or 8 years, let us say. Then, so here usually the temperature would be ambient temperature only, because only during the short term aging you can see that bitumen would be subjected to higher mixing temperature and compaction temperature. Here after laying in service you will have normal pavement temperature. So only the exposure of oxygen is what going to cause the aging. So when I want to understand the aging in the servicing, that means that could have been already mixed, that could have been already exposed to the mixing temperature, then only we could have placed into the field and compacted. That means short-term aging has been already done for that bitumen, then it will be subjected to the long-term aging. So anytime if you want to understand the long-term aging, first expose that bitumen to the RTFO process which we have explained previously. Then take that RTFO sample, now fill into the containers like this. For 20 hours, expose the pressure to 2.5 megapascals. This pressure is to simulate the exposure of oxygen to the bitumen. Then you can conduct this test at multiple temperature depending upon the location where you wanted to use this bitumen. If it is a moderate temperature 90, if it is a low temperature 90, moderate 100, higher means 110. Then you take out that after 20 hours, because you are conducting it at around 100, 110 or 90, it would be difficult to take this bitumen out of this container. Therefore, for 15 minutes, keep in the oven. So then it will become like a liquid or fluid. So when it becomes like a fluid, then you can conduct it easily. So there is another thing is that sometimes there is a probability of having few gases in that bitumen. So try to use the degas technique to remove those air voids. So the last two tests would be, one is purity test and safety test. So after this we will see few questions and we will wind up the session. So purity test, as we have already discussed, to understand the quality of the bitumen, we try to dissolve that bitumen into either carbon disulfide or trichloroethylene. So we do not want more than 1% of the remaining. So 99% we wanted the bitumen to be dissolved. And another is the safety test, as we have already discussed, which is a flash and fire point test. So we need to know the what is the flash and fire temperature of the bitumen. That means our workers are when we are handling the bitumen, we should not heat the temperature beyond that temperature. This is for the safety of the users. So let us see few questions on the concept that we have discussed till now. Which of the following statements are true? Tar is obtained from destructive distillation of coal or wood. I think this is correct. Temperature susceptibility of bitumen is higher than tar for bitumen. Let us say we do not know whether it is correct or not. Bitumen is obtained by destructive distillation. We know bitumen is obtained by fractional distillation. So we can say this is wrong. So what could be the expected answer? Anyone? You can type in the chat box. Let us say this is A, B, C, D. Is the temperature susceptibility of bitumen is higher than tar or not? If the B is correct, then it will be both A and B. If the B is wrong, the option will be only A. Yes, you can type in the chat box. Anybody answering? I think you audience can type now. Any guesses whether B is correct or not? So as we have already discussed, core is the tar is actually from the destructive distillation of coal or wood, and this process is actually done in the absence of oxygen. So it actually gives the harmful gases. That is one of the reason why we use the bitumen, and this tar is extremely temperature susceptible than the bitumen. So the option B is actually wrong. That means only option A is correct, which means tar is obtained from destructive distillation of coal or wood. And the second question is, The first product obtained below the fractionating column during distillation of crude oil is called, as we have discussed. So initially when you have the crude oil and it is subjected to higher temperatures and also the pressure more than the atmospheric pressure, there is a residue at the bottom. Whatever is having lower boiling points, they will be evaporated and collected, but those who are having higher boiling point which cannot be separated, they remain at the bottom and we call that as long residue. And the third question, which of the following elements are responsible for the interaction of bitumen with other surfaces? So this one also we have discussed, mostly the heteroatoms. So the heteroatoms are the one which we call as polar groups or functional groups, which are responsible for reacting the bitumen with either aggregate surfaces or with other any molecular structures. So here carbon hydrogen is not a heteroatom. Sulfur carbon hydrogen, we know carbon hydrogen is not. That means option B also not. So here sulfur, oxygen and hydrogen. As the hydrogen is present, this is not. Yes, the 4 sulfur, oxygen, nitrogen is the correct. Which of the following act as the peptizing agent in the bitumen colloidal system? We know bitumen colloidal system is the combination of maltines and asphaltenes. So asphaltenes actually have a medium called maltines. So these maltines are peptizing agents for asphaltenes. So when I take SARA, these 4 are the components of bitumen, SARA fractions. Okay. We know SAR, saturates, aromatics, resins are maltines, together called as maltines. Asphaltenes are separate. So here the question is, which of the following act as a peptizing agent? We know maltines are acting as a peptizing agent or dispersing agent in the bitumen colloidal system. Okay, option B. If a bituminous surface in the field shows serious cracking, the anticipated penetration of extracted bitumen would be. This also we have discussed. If the penetration is less than 20, is it a severe crack? 20 to 30, what is it? Greater than 30, what is it? So here the question is serious cracking. Any guesses? To have serious cracking, the penetration should be very low. When I say penetration is very low, bitumen is very stiff. So having very higher stiffness is not favorable at temperatures like 25 and lower and intermediate temperatures. Let us say at 60 degrees, having more stiffness is very favorable condition. We can avoid the rutting there. But at intermediate temperatures like 25 degrees, if the bitumen is very stiff, there is a problem of bending. Thereby cracks can be formed. So at less than 20 degrees, if the penetration is less than 20 degrees, so there is a probability of having serious cracking. Yes, correct. And another question. So a manufacturer of capillary viscometer used an oil for calibrating the capillary tube. The time required by the oil of viscosity 320 poise to cross the, okay, what has been given here? Capillary viscometer used an oil for calibrating. That means calibration details are given. So for the calibration oil, time required T1 and the viscosity eta 1. So it is 320 poise and the time required is 4 seconds. If the time taken by bitumen, let us say now you have bitumen. The time taken is T2, which is nothing but 30 seconds. So what is the viscosity they are asking? So we know eta 1 by eta 2 equal to T1 by T2. So by substituting, it is just a calculation. you will get the answer as 2400 poise. And another question is, in the temperature susceptibility method proposed by the Pfeffer and Van method, the penetration of bitumen at the softening point is assumed to be. If you remember, when we calculated the penetration index, in the formula, we were calculating the slope. So when I have a graph like this, log of penetration versus temperature, in this the slope is nothing but 8. So to calculate this, we have a formula which is empirical method. In that, if you know the softening point of bitumen, let us say 50 degrees, one thing is you can directly calculate the penetration of the bitumen at the softening point, and another assumption they have made is yes, the option is 800. The another assumption is 800. So which of the following aging process incorporates slow crystallization of waxes? Okay. So one is oxidation, is when the bitumen is subjected to only oxygen. Voltization is when the lower molecular weight oils are evaporated. Steric hardening is at ambient or normal temperatures. Within the bitumen, the resins and asphaltenes, they themselves will react and they will reorient their molecular structure. That is what called as steric hardening. Another is exudation of oil, where the lower viscosity oils will be absorbed by the aggregates with higher porosity. So in addition to these, when we store the bitumen in the ambient temperature, we call that the steric hardening will happen. So in addition to the steric hardening, where the reorientation of molecules can be formed in the Sara fraction, so this R and A, resins and asphaltenes, are polar in nature. So these polar groups have heteroatoms attached to that. So they have the probability to react among each other and they will reorient. That is one way of having steric hardening. Another way is, let us say, if the bitumen has any kind of wax content, then it can slowly crystallize at the normal temperature, which can actually cause the aging. So steric hardening is one of the reasons. The increase in stiffness of bitumen with time usually follows. This, if you could have seen one of the model. So as per the previous researches, what was observed is, if the bitumen stiffness increases with the time, then that behavior is usually following a hyperbolic model. That's correct. So, are there any questions on the topics that we have discussed today? Or any doubts, or do you want me to discuss anything extra? You can unmute yourself and ask if there are any doubts.
Madam,
Sir.
so while calculating the specific gravity by API method,
Hmm.
so the specific gravity of the water at the temperature is to be considered. So
Hmm.
in our assignment, it is mentioned that the specific gravity is 23 degrees Celsius.
Hmm.
So normally, but we are taking this value as a one,
Yes. That is not at
specific gravity of the
23.
water.
Hmm.
But if you look at the difference 20, 23 or 25, there is a little variation after the 9, 8 or 9, 9. Okay.
Yes, sir.
So can we take that as a one?
Usually, to be frank, perfectly speaking, it will not be 1 at 23. So we should not take. But in cases where they haven't mentioned, then we are supposed to consider it as 1.
Thank you, madam. Thank you. Yeah.
Any other questions? Okay then. Thank you for joining. We'll close the meet.
Thank you, madam, for sparing your valuable time and nice explanation of the all the doubts
Thank you, sir.
and taking the questions. Okay.